This section sets out the basic accounting of quantum Shannon theory. Information counts what you cannot already predict. The quantum version counts what no choice of measurement can inflate. The coin fixes Shannon's bit as a measure of surprise, with voltage beside the point. A physical bit holds the outcome, and the entropy measures the randomness. Then Bob's ensemble of spin-up along Z and spin-up along X breaks the analogy. A Z measurement yields 0.81 bits, while an X and Z measurement yields only about 0.6. What Schumacher compression later realizes operationally at about 0.6 qubits is the minimum over Sharp measurements. Disturbance is the reason the minimum exists. Learning less means disturbing less. Everything downstream is bookkeeping in 3 currencies: the C-bit, the Q-bit, and the E-bit. The capacity theorems are the exchange rates between them. The qubit channel is the strongest of the 3, since it generates the other 2 and neither of them generates it. This part explains what Shannon's classical theory settles and why the book puts it first. Shannon's founding move is to sever information from meaning. What a source is becomes irrelevant, and only how often it surprises you matters. A message drawn from an alphabet you can predict carries nothing. The whole quantity of information in a source is the entropy, written H, of its distribution. That number measures the ignorance the symbols resolve. The symbols themselves hold no such property. Everything downstream, compression, transmission, error correction, falls out as bounds set by that single scalar. The chapter's function in the book's arc is to establish this classically, so that the quantum chapters have a fixed point to deform. Replace probability distributions by density operators, and the same skeleton reappears. Bent. Noiseless means isolated, and isolation buys no determinism. This section explains why the chapter's first move is to split 2 kinds of randomness that classical information theory treats as one: the casinos, which is ignorance, you could in principle remove, and the uncertainty principles, which survives complete knowledge of the state. Everything else in the chapter is bookkeeping for that split. States become unit vectors, evolution becomes unitary, measurement becomes the one place where a determinate description yields an indeterminate outcome, composition becomes the tensor product. The idealization is what makes the rest of the book measurable. Noise enters later as coupling to a system you do not hold, so the uncoupled theory must come first in order to say what was lost. Entanglement arrives already here, inside the noiseless theory, as the resource with no classical shadow. This section explains what the theory becomes once perfect knowledge of a state is given up. Perfect knowledge is an unaffordable assumption. Drop it, and the theory has to be rebuilt around one object and one arrow. The object is the density operator, which carries the entire observational content of an ensemble, so 2 ensembles sharing one operator are indistinguishable. The arrow is the quantum channel, and the thesis of the chapter is its universality. Preparation, measurement, discarding, unitary evolution, and classical channels are all channels. That is the claim of section 4.6, titled Quantum Channels Are All-Encompassing. Classical probability reappears inside the same formalism as the diagonal restriction, inside the same formalism as the diagonal restriction. The noiseless theory of Chapter 3 survives only as a special case. That closure is what makes a Shannon theory possible at all, because capacity must be defined over a composable class of noisy maps. This section explains why a noisy quantum theory sits inside a noiseless one rather than beside it. Noise is a restriction, never a primitive. Every density operator rho on a system A is the reduced state of some pure state psi, shared between a reference system and A, and every noisy channel is an isometry into system plus environment, followed by discarding the environment. So Chapter 4's noisy theory sits inside Chapter 3's noiseless one, as the case where you cannot see everything. The generalization ordering reverses, which is what the chapter is for. What keeps this bookkeeping rather than metaphysics? All purifications of rho on A are related by an isometry acting on the purifying system alone, so no local prediction depends on which one you name. The environment then becomes a legitimate second output. The complementary channel and mixedness measures entanglement with whatever was discarded. This section explains 3 quantum protocols and the exchange rate bookkeeping that connects them. 3 resources, a classical bit channel, a qubit channel, and an EBIT. Everything Alice and Bob do with them becomes bookkeeping in a single currency. Each protocol is written as a resource inequality. Entanglement distribution, 1 qubit channel is greater than or equal to 1 qubit channel. 1 qubit channel plus 1 EBIT is greater than or equal to 2 classical bit channels. Teleportation, 2 classical bit channels. Teleportation, 2 classical bit channels plus 1 EBIT is greater than or equal to 1 qubit channel. Inequalities, Jane. So optimality costs no new physics. Compose a hypothetically better rate with teleportation, and 1 qubit channel manufactures unbounded quantum communication, hence superluminal signaling. That is the chapter's office in the book's arc. It fixes the noiseless exchange rates, so every later chapter is one substitution. Replace a perfect resource with a noisy channel, N, and the inequality becomes a capacity question. This section explains why teleportation and superdense coding fail to be inverses, and what new resource closes the gap. Teleportation and superdense coding look like inverses, and the appearance fails. Teleportation's 2 classical bits cannot pay back the EBIT it also burns. Wild's move is to mint the missing denomination rather than declare entanglement free. That denomination is the coherent bit channel, a classical bit whose environment Alice keeps, copying basis states, while preservant superposition it sits strictly between a qubit and an EBIT. Coherify both protocols and they close into an exact resource equality. 2 uses of the coherent bit channel equal 1 EBIT plus 1 noiseless qubit channel. The chapter exists to establish that exchange rate. Later capacity theorems whose output is private classical bits get upgraded to coherent ones and cached directly into quantum communication, with the EBITs cancelled catalytically. This part explains how the unit resource capacity region turns 3 protocols into a geometry. A protocol becomes a vector, composition becomes addition, and optimality stops being a property of any single protocol. It becomes the shape of a cone. Teleportation, superdense coding, and entanglement distribution sit at -2, 1, -1, then at 2, -1, -1, then at 0, -1, 1 in the space whose 3 axes are C, Q, and E. The sign marks consumed against generated. The sign marks consumed against generated. Their positive span is the achievable region. The chapter's claim is that this cone is already everything. 3 protocols exhaust the noiseless resource theory, and the converse falls out of walking. The 8 octants under 3 physical postulates rather than out of any coding argument. Its role in the book's arc is to hand the later trade-off capacity theorems, in Chapter 25, a fully solved corner to sit inside. This section explains why the theory needs a metric on quantum states before any coding theorem can be stated. Every coding theorem later in the book is an approximation claim, so the theory first needs a way to measure how far apart two states are. Wild builds two such measures, and the pairing of them is the point. Trace distance is the largest probability gap any single measurement can open between rho and sigma. Fidelity is the best overlap achievable over purifications. Each of the two is defined by an optimization over an operational task rather than by matrix entries. That is why both contract under any quantum channel. Processing cannot manufacture distinguishability. Fuchs and Van de Graaff then sandwich each measure inside the other, so the statement that the error vanishes in the limit means the same thing, whichever measure you hold. The chapter is Shannon's epsilon tolerance from Chapter 2, fitted with a quantum carrier. This section builds every information measure in the chapter out of a single primitive. That primitive is surprise, minus the logarithm of the probability of x, with the logarithm chosen precisely so that independent experiments add. Entropy is the expectation of surprise. Every later measure is that same expectation taken relative to what somebody already holds, condition on Bob's side variable, and you get the entropy of x given y. Difference the two and you have what the correlation y, difference the two and you have what the correlation was worth. Wild defines these quantities around parties instead of around distributions. Alice holds x, Bob holds y, and entropy is Bob's uncertainty before learning. That choice of framing is why the quantities read later as answers to operational tasks rather than as formal conveniences. The chapter is the classical rehearsal of a construction that runs again, quantum mechanically, in Chapter 11, where conditional entropy goes negative and the agent reading breaks. This section explains what changes when classical information theory is carried over to quantum systems. Substitute the density operator for the probability distribution, and every classical entropy definition carries over unchanged. The chapter exists to show that exactly one thing breaks in the transfer, and that the break is the resource. Conditional entropy, the entropy of A given B, is defined as the joint entropy of A and B minus the entropy of B. In the quantum case, this quantity can go negative, a part more mixed than the whole, which never happens classically. Its negation, the coherent information, obeys its own data processing inequality. Capacity theorem. The tell is arithmetic. A maximally entangled pair registers 2 bits of quantum mutual information where classical correlation caps at 1 bit. The information qubit, distinct from the physical qubit, is the unit installed here. This section explains how monotonicity of relative entropy becomes a statement about reversal. Monotonicity of relative entropy says a channel can only make 2 states harder to tell apart. Chapter 12 turns that inequality into a statement. About reversal, the entropy drop is bounded below by minus the logarithm of the fidelity between rho and the composition of the recovery channel with the original channel applied to rho. The recovery channel is explicit and depends only on sigma and the channel n. It is the rotated Petz map. Little loss therefore means the channel is nearly undoable. Equality means it is undoable. Its office in the book's arc is to convert every converse-proof instrument of the previous chapter, strong subadditivity, joint convexity, non-negativity of discord, the Holovaux bound, from a bare inequality into one carrying an operationally meaningful remainder. This section explains how every information quantity attached to a quantum channel in this chapter is built, and what has to be true before any of them counts as a capacity. Each one comes from a single recipe. Send half of a state through the channel, evaluate a static entropy from chapters 10 and 11 on the input 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 and output pair, then maximize over inputs. The real work of the chapter is the gate that follows the recipe. Such a measure means something only if it is additive across independent uses of the channel, because additivity is what lets a single channel use fix the capacity. The stakes land in a constructed counterexample. A deliberately misweighted variant of mutual information sits strictly below mutual information for every finite block length, and yet regularizes to exactly it. The limit blurs distinct one-shot quantities together, so a regularized formula can never identify which task it measures. The closing table is the verdict. Additive for all channels, additive for some, or additive only for degradable ones. This section explains how entropy stops being a number and becomes a region of sequence space. Entropy names an average. Typicality turns that average into a set. Draw n symbols independently and identically distributed, and the sample entropy, meaning -1 over n times the logarithm of the probability of the sequence, concentrates on h of x. Sequence space then cleaves into an exponentially thin band of near equiprobable strings holding almost all the mass and everything else. Shannon's compression becomes a question with a yes or no answer. Typical, keep. Atypical, discard. The error stays non-zero at every finite n and vanishes in the limit. The generative primitive here is measure concentration. A smooth function of many independent variables is nearly constant, and the region where that holds is small enough to count. This chapter is the classical rehearsal. The quantum theorems repeat the same move with a subspace standing where the set stood. This section explains how classical typicality survives the passage into quantum information, and what that passage costs. Spectral decomposition converts a quantum source into a classical one. The eigenbasis of the n-fold tensor power of ρ is orthonormal, so its eigenvalues are already a probability distribution, and the typicality of chapter 14 transfers unchanged. The chapter is that single move plus its price. The price is measurement. Classically, asking whether a sequence is typical means reading the symbols. Quantum mechanically, reading destroys. So typicality becomes a subspace, and the question becomes a two-outcome projector, a measurement almost certain to answer yes, and therefore almost non-disturbing. The boundary that exposes the structure is the sizing. The subspace is sized by the entropy of the spectrum of ρ, and not by the entropy of the ensemble that prepared it. A source emitting ket 0 and ket plus with equal probability spans a subspace of dimension 2 to the power 0.6n, far below the full 0.6n, far below the full 0.6n, far below the full. This part explains the packing lemma as a counting statement. Distinguishability is a counting question. The four conditions say only one thing. Each state lies in the code space, the projector pi. Each state lies in its own code word projector, pi sub x. Each pi sub x has dimension at most d. and pi sigma pi is less than or equal to pi divided by capital D. Together they say small subspaces of size d packed into a space. Whenever the number of messages is much less than capital D divided by D, the messages stay decodable. The chapter's work is to make that ratio the entire content of a coding theorem. Random codes, the square root measurement, the error analysis are machinery serving it. It is stated one shot, with no channel anywhere inside it. HSW capacity and entanglement. Assisted capacity arrive later by naming which subspaces play capital D and which play D, 2 to the n times h of b, divided by 2 to the n times h of b, given x equals 2 to the n times h of b. This section explains the covering lemma and how it inverts the packing lemma. Packing asks how many states a receiver can tell apart. Covering asks how few suffice to make the receiver unable to tell anything at all. The two lemmas share the same hypotheses: a total projector, code word projectors, and ensemble. Covering simply reads them in the opposite direction. Alice draws uniformly from a small random subensemble whose average density operator already approximates the true average. Eve, holding only that average, learns nothing. The shortfall is measured as obfuscation error, the trace distance between the fake expected state and the true expected state. The full state qubit example is the whole idea in miniature. The pair ket 0 and ket 1, and the pair ket plus and ket minus, each average to pi, so 2 bits of ensemble hide 1 private bit. Randomness is priced as a resource here, and it is what the private capacity chapters will spend. This section explains Schumacher compression, the quantum counterpart of Shannon's source coding theorem. Shannon's theorem gave the entropy an operational identity, the compression limit. Chapter 18 does the same for the von Neumann entropy, H of rho, and the whole move is one substitution. The typical set becomes the typical subspace. The source emits the state psi sub x with probability p of x. Compressing the labels x costs h of x, and that squanders the quantum channel, since classical wires would have sufficed. Non-orthogonal states overlap, so the ensemble occupies fewer dimensions than it has members. Alice projects onto the typical subspace of the n-fold tensor power of rho. An isometry carries its roughly 2 to the power n times h of rho dimensions into qubits, and Bob inverts it. H of rho is less than or equal to h of x, with strict inequality exactly when the states overlap. This is what makes qubit a measured quantity rather than a name. This section explains what happens to entanglement when you are restricted to local operations and classical communication. Under that restriction, pure bipartite entanglement collapses to a single scalar currency. Whatever angle theta tilts the state phi theta away from maximal n, copies concentrate. A Hamming weight measurement lands the state inside one typical tight class. And the surprise carrying the whole chapter is that such a class is exponentially large, so it is already a maximally entangled state of Schmidt rank 2 raised to the power n. Dilution is that protocol rung backwards through Schumacher compression plus teleportation. Conversion is thus reversible in the many-copy limit, at a rate given by the entropy of A in psi, divided by the entropy of A in phi. Only the ratio of entropies survives, never the structure of the states themselves. The epoch takes unit status because its entropy equals 1. Chapter 18 fixed the operational meaning of the word qubit. This one fixes the word ebit. This section explains classical communication over a quantum channel and where the quantum advantage actually lives. Measure each channel output as it arrives and the quantum channel collapses into an induced classical one. The extractable rate is then the accessible information, Shannon's theorem applied to the conditional distribution of y given x, which is the trace of lambda sub y times the channel n applied to rho sub x. Nothing quantum survives that step. The chapter's whole move is to postpone the measurement. Decode collectively across all n outputs at once, and the achievable rate rises to the whole of O information, chi of n. Quantumness buys capacity at the decoder. The whole of O, Schumacher, Westmoreland encoder, stays product states throughout. This is the book's first dynamic task, a channel connecting Alice to Bob, rather than a static resource. The boundary that reveals the structure? The converse is multi-letter, so Chi names the capacity only where it is additive, and Hastings, in 2009, showed it sometimes is not. This section explains what changes when Alice and Bob are handed free. Entanglement, an unsolved capacity problem, becomes a solved one. Without entanglement, the classical capacity of a quantum channel stays open. The whole-level information requires regularizing, and for some channels it is provably not the capacity. Grant Alice and Bob an unlimited supply of EBITs, and the answer collapses to a single letter, the channel's mutual information, maximized over pure bipartite inputs, concavity in the input state over a convex set of density operators makes every local maximum global. So the capacity becomes an efficient convex program rather than an inefficient convex program, rather than an unevaluable limit. Underneath sits one recognizable move. Chapter 21 names it a glorified superdense coding applied to noisy quantum channels. Entanglement buys tractability. This section explains why one quantity decides what survives when a quantum protocol has to run on imperfect resources. Quantum information's hardest problems all have the same shape. You hold a resource that is imperfect, a noisy channel, a partially entangled state, a source with correlations you did not choose. You want to run a protocol that assumed a perfect one. Coherent information is the quantity that decides what survives. The chapter's move is to stop treating noisy channels and noisy states as separate theories. A channel is a state by the Choi-Jamilkowski correspondence. An entangled state is a channel you already ran. So every protocol built on clean resources, teleportation, dense coding, entanglement distribution becomes a father or a mother protocol from which the noisy versions fall out by composition. The achievable rate regions are then the same polytope seen from different vertices. What this chapter is for, in the book's arc, it converts the resource inequalities of the earlier chapters into a working calculus over imperfect resources, so that capacity theorems become bookkeeping rather than separate proofs. This section explains private classical communication as a subtraction of resolving powers. Alice builds a doubly indexed codebook carrying the message M and a junk variable K, and each index is spent on a different opponent. Bob must resolve the whole pair, which consumes the mutual information between X and B. Randomizing over K must blanket Eve's typical subspace, which consumes the mutual information between X and E. What survives, the mutual information between X and B minus the mutual information between X and E, is the private rate, packing against covering. The two lemmas pulling in opposite. The chapter's place in the arc is the quieter half, since Eve's state is constant in M, superposing private code words leaves her nothing to steal. A private classical code coheres into a quantum one, and privacy becomes the road to quantum capacity without catalytic entanglement. This section explains why privacy and quantum coherence turn out to be one resource seen twice. What Eve cannot learn, Bob can hold coherently, and no, cloning is what forces that complementarity. A subspace kept secret from the environment is exactly a subspace where quantum information survives. The chapter's move is to take the private classical codes of Chapter 23 and cohere them, run the private code in superposition. Secrecy then becomes decoupling, and the rate becomes the coherent information, the entropy of Bob's system minus the entropy of Eve's system. That entropy difference has no classical shadow. This is the point where the two Shannon theories part. The sting arrives at the end. Coherent information can be strictly superadditive, and two individually useless channels can superactivate. Quantum capacity admits no single-letter formula.